Howdy everyone, welcome back for our chapter 16 example problems where we'll be looking at some Ka and Kb information when we're doing equilibrium reactions involving weak acids and weak bases and how that all works. So we'll start out with something simple, but it's very important still that we need to be able to identify the conjugate pairs. Many times in a problem, if we mess up the conjugate pairs, then we might be plugging the wrong numbers in and we may have difficulty finding the right information of what we're supposed to do. So the key is to say, okay, look between reactants and products and say what species in the reactants is giving up an H+, because that's going to be the acid that donates. And then what species accepts that H+, that'll be the base. So if we look here, we start with ammonium and cyanide. We end with hydrocyanic acid and ammonia. So we say, well, wait a minute, we have NH4+, we go down to NH3, there's the donation of an H+, so this must be the acid. And then the cyanide becomes HCN, that took in the H+, that must be the base. But the key though is we're doing the whole conjugate pair. So the resulting product after you donate the proton is the conjugate base of the acid, and the product that results after you accept the proton must be the conjugate acid of the base. So we look here and say if NH4 is the acid, then what looks like NH4 just minus an H+? Well, it's the ammonia, so that will be our conjugate base. And then we look here, here's the base with cyanide, there's the hydrocyanic acid that accepted the H+, that must be the conjugate acid. The way to double check is think to yourself, if I wrote this reaction backwards, if these two were my reactants, which one would be the acid, which one would be the base? And oh, HCN, it would donate. That must be an acid. Ammonia, oh, it's going to accept that H+. It must be a base. Just in this case, they're the conjugates. Same thing happens over here. We have trimethylamine with water going to a trimethyl ammonium, and hydroxide. So we say, okay, wait a minute, this amine here, it's just N, but now it's NH+. This accepted an H+, that must be the base. That means water must be the acid, and yep, it got rid of an H+ over here. So then the conjugates switch. Okay, the trimethylamine with the H+, that must be our conjugate acid. The hydroxide must be the conjugate base. And again, if we think to ourselves, let's write it backwards. Right, this thing is going to get rid of the H+, so it must be the acid. The hydroxide is going to accept the H+ to become water. It mmust be a base. So, like I said, hopefully fairly straightforward, but it's always good to remind ourselves how that works. All right, now for some of the math stuff. We're going to look at a typical Ka and pH problem where we're saying, okay, if we have a weak acid and we're given a Ka, can we get those concentrations? Now, a lot of times you're asked to find the pH, which means, okay, find the concentration of H+, and then just take the negative log. Here they just want the concentrations, but we're going to do it two ways. We're going to do it with the shortcut and without. Typically, and I know I did check the homework that I assigned for this, I pick ones that can use the shortcut because that's what we like. This one in particular cannot use the shortcut, so we're going to try the shortcut first, find out why it doesn't work, and then we'll do it the full way on the next slide. So it says we've got our Ka for chlorous acid, and they want to know what are the concentrations if the initial chlorous acid molarity is 0.0125 molar. And so for the shortcut, we say, oh, Ka is equal to x squared over Ha, and we just keep it Ha. So in this case, that would be 1.1 times 10 to the minus 2 equals x squared over 0.0125. That means x squared is going to equal 1.1 times 10 to 1.01 times 10 to the minus 2 times 0.0125. And then, so that's x squared is 1. What do we got? 26 times 10 to the negative 1, 2, 3, 4, which means x, when we square root that, is 0.11, 0.0 112 molar. And we see right there, there's the problem. X is not negligible compared to initial. Our initial's 0.0125 and we got 0.0112. It's 90%. That can't work. So we can't use the shortcut here. We've got to go ahead and use the quadratic, where we'll say, okay, if we make up our ice table, we have HClO2 is in equilibrium with H plus and ClO2 minus. Make up our little ice table over here. Good drawing practice with tables here. So this is 0.0125. These are zeros. We're going to be minus x plus x plus x. So we're still going to have x squared on top, but now it's going to be 0.0125 minus x, and we have to keep that. We saw from the shortcut that can't work. So now when we set it up, we get that the 1.1 times 10 to the negative 2 must be equal to x squared over 0.0125 minus x. When we rearrange all this, we will get x squared, let's see, that'll become a negative, so plus 1.1 times 10 to the minus 2 x, and then what is that number? 1.1 times 10 to the minus 2 times 0.0125. That's positive, but the movement make it negative, so negative 1.38 times 10 to the, what would that be, negative fourth, it looks like. And then that all equals 0, and we've got to solve for x. That means we've got to use a quadratic. So let's see, the quadratic is that x equals negative b, so negative 1.1 times 10 to the negative 2, plus or minus the square root of b squared, so 1.1 times 10 to the minus 2 squared, so that's 1.21 times 10 to the negative fourth, minus 4ac, so that's 4 times that, so 1.38 times 10 to the minus fourth times 4, let's see, it's a negative there, minus negative, so it's plus 5.52 times 10 to the negative 4. You can see it's getting ugly already. That's why we use the shortcut if we can. All over 2a, so just 2. Okay. So let's go ahead and put those numbers together in the middle. 1.21 times 10 to the negative fourth plus 5.52 times 10 to the negative fourth. All right. We get 6.73 times 10 to the negative fourth. We take the square root of that. We get x equals negative 1.1 times 10 to the negative second. Now, because this is already negative, we know the minus can't work. We can't have a negative concentration, so I know it has to be plus. And it's plus 2.59 times 10 to the negative second. And then it's all over 2. And then if we just simplify this out, so that's minus 1.1 times 10 to the negative second, divide it by 2, x equals 0.00747, it looks like. All right. And so that's going to be two of our numbers. That's going to be H plus, and that's going to also be the chlorite, because they're both X's, and then the equilibrium concentration of the hypochlorous acid is going to be the initial minus that, so 0.0125 minus 0.00747, and so we get 0.0 looks like 050 based on the 4 decimals here, so 4 decimals here, molar. And that makes sense. If we plug those numbers in, 0.00747, if we square that and then divide by 0.005, yeah, we get 1.1 times 10 to the minus 2. So it's good to kind of double check those numbers, make sure that if you plug them back in, do you get what you're supposed to get? In this case, yes. If we were asked to find the pH, then we'd say, okay, take that H plus of 0.00747, take the negative log of it. In this case, the pH would be about 2.13. All right, so hopefully you don't have to do that. You're not going to do that on a test. I even try to avoid it on homeworks most cases, but if you are forced to do that because of a fairly large Ka value, like this one here, 10 to the minus 2, or because of a very dilute acid, right? If this is a small molarity, then it's also more likely to happen. And in this case, combination of the two, you're definitely going to have to use the quadratic. Have fun remembering Algebra 1. All right, one more example problem we want to look at, which is for weak bases. So that if we're given an information about a weak base, can we calculate necessary concentrations? Can we still figure out pH? And so for this one, we'll just do a quick one of 0.1 molar sodium hypobromite. And the information that we're given, when they say, oh, look it up in the back of the book, or if it's provided in the problem, is that the Ka, not for hypobromite, but for the acid, hypobromous acid, is 2.5 times 10 to the negative ninth. You say, okay, but wait, that's not what I have. Remember that the key relationship here is that Kw must always be equal to Ka times Kb, which means, oh, we want to find Kb. That means Kb is equal to Kw divided by Ka. And so, oh, we know Kw, it's the 1 times 10 to the negative 14th. We have Ka for that acid. We were given it to us. And so that's how we can find the Kb of the conjugate base. In which case, now we can just write our normal equation for a base. We can say, okay, we got hypobromite. And if we react that with water, we will get the hypobromous acid plus hydroxide. That means if we write our Kb expression, it'll be equal to HBRO times hydroxide all over the hypobromite concentration. But we can, again, simplify that. It's going to be x squared over, in this case, the initial base concentration. We're going to assume, okay, let's double check our Kb, but if it's small enough, because that molarity is pretty good, we should be able to not have to do minus x. We should be able to just plug in the initial and it would work out the same. So let's go ahead and do that. Let's find out what Kb is going to be. So in this case, Kb will be 1.0 times 10 to the negative 14th. That'll be divided by the Ka of the conjugate, so 2.5 times 10 to the minus 9th. And if we do that, 1 times 10 to the negative 14th divided by 2.5, 10 to the minus 9th, we get 4.0 times 10 to the negative 6th. Okay, and yeah, 10 to the negative 6th, that's a pretty small number. It seems safe to assume we can use the shortcut. We'll double check it at the end, but I think we'll be good. So now let's go ahead and plug our numbers in. So 4.0 times 10 to the negative 6 for the Kb will equal x squared over, and our initial is, okay, with this one, it's a ionic compound. So we just see, okay, how much does it break up? If it's 0.1 molar sodium hypobromate, we see there's just one hypobromite, so it's 1 to 1. It's still 0.10 molar. So do watch out for that. In some problems, if there's a 2 or a 3, you got to take your initial molarity and say, oh, right, there's 3 of them. It's going to be triple that molarity. There's also problems sometimes where you might have 2 salts that you have to add up to say, what's my total molarity of my conjugate base? But in this case, just 0.1 molar. If we solve for x squared, then that'll be, well, times 0.1. So that'll be 4.0 times 10 to the negative 7th. And then when we square root that, that means x is equal to 6.3, let's see, sig figs, 2 sig figs, 6.3 times 10 to the negative 4th molar. And so, yeah, we compare that to 0.1 molar. Yeah, x is much, much smaller than the initial. this was a fair assumption. We don't have to worry about anything. And that's the first answer. That's hydroxide, because we said, oh yeah, hydroxide's up top. It's one of the X's. Then they ask us to find the pH. And so we can remember, wait a minute, we can get the pOH because that's the negative log of our hydroxide concentration. So that'll be the negative log of 6.3 times 10 to the negative fourth molar, which will equal, looks like 3.20 for sig fig. So that's the pOH. And then we remember, hey, wait a minute, the pH plus the pOH must always add up to 14, assuming room temperature water. So if the pOH is 3.20, that means the pH must equal 10.80. And so there's your second answer for this problem. So when you're doing things like this, just again, always watch out. What's my actual molarity of the conjugate base, depending on what the formula is. Always use the Ka to figure out the Kb. And then, yeah, when you get your answer for hydroxide, just give it that little quick double check. Is this number small enough where it doesn't really affect that initial concentration? In this case, yeah, no, it would be 0.99937. Yeah, that's 0.10. That rounds fine. So yeah, so there's some help for chapter 16, hopefully. And moving forward to chapter 17, a lot of this stuff will also be valid. So keep this in mind. Rewatch it as you need to. Ask questions as you need to. And I'll see you soon. Have a good day.